If you were to go as far out into space as you can imagine, what would you encounter? Would there be a limit to how far you could go, or could you travel a limitless distance? Would you eventually return to your starting point, or would you continue to traverse space that you had never encountered before? In other words, does the universe have an edge? And if so, where is it? What lies beyond that? What about the unobservable universe? Is there any way to use what we know and measure about the universe we inhabit to answer the question of whether it's finite or infinite, about whether what we know of as the universe goes on forever, or whether there's some limit to what's out there? These questions have fascinated scientists for ages. But now, thanks to the James Webb Space Telescope, we can peer back over 13.5 billion years to see the first stars and galaxies forming out of the darkness of the early universe, thereby unlocking the secrets of the universe. However, in addition to wowing the world with breathtaking glimpses of galaxies from cosmic dawn, the $10 billion time machine also leaves scientists scratching their heads as its discoveries challenge the perception and understanding of the universe. They raise world-shattering points about how the expansion of the universe seriously factors into the way we calculate the size of the universe. Join us as we dig deep into how James Webb just revealed the true scale of the universe. First off, let's face it, space is big. That's why we call it space. But how big is big? That's relative. When an astronomer says something is nearby, they might mean it's a few million kilometers away if they're talking about asteroids, or a few tens of trillions for stars, or a few tens of quintillions for galaxies. No matter the destination, it's a long walk. We make it easier on ourselves by using huge units to measure distance, such as a light year. The distance traveled in a year by light, the fastest thing in the universe. A light year is about 10 trillion kilometers. But that's still fairly abstract to the typical person reading casually about nearby exoplanets or distant galaxies. One way to better grasp this scale is to take it step by step. The moon is the closest astronomical object to us in the entire universe. On average, across its orbital path, it's about 380,000 kilometers from Earth. That's already a pretty long way. Nearly 30 Earths could fit side by side over that distance. Or think of it this way. The Apollo astronauts, traveling faster than any human before them, took 3 days to reach the moon's vicinity. The sun is about 400 times farther away from us than the moon is, 150 million kilometers. How far is that? If you could pave a road between Earth and the sun, it would take you about 170 years to drive there at highway speeds. Better pack a lunch. A commercial jet would be better. It would take a mere 17 years. When we work with objects inside the solar system, it's convenient to use the Earth-Sun distance as a kind of cosmic meter stick. We call it the astronomical unit, and it is defined by the International Astronomical Union as exactly 149,597,870.7 kilometers. To give you some perspective, let's begin by considering local space. Assume that the distance between Earth and the Sun, known as 1 astronomical unit, is 1 centimeter instead of its actual 149,597,877 kilometers. In all of human history, mind you, we have physically traveled an imperceptibly small fraction, then, of that 1 centimeter. You can think of a scale model solar system in your room, your neighborhood, and your town. On that scale, Jupiter would be 5 centimeters from the Sun. Keep moving off, say, to the right, and imagining the relative distances. Saturn would be 10 centimeters from the Sun, Uranus 19 centimeters from the Sun, and Neptune 30 centimeters from the Sun. Little old Pluto would typically be about 40 centimeters from the Sun. However, on this scale, the physical diameter of the solar system is far larger than that. The outer edge of the Oort cloud, the enormous shell of perhaps 1 trillion comets, would lie 10 football fields away. And we have, thus far, traveled a tiny, almost invisible fraction of that original 1 centimeter. And that's just our solar system. The nearest star, Proxima Centauri, is 4 times farther away than the outer shell of the Oort cloud. The enormous gap between even the nearest stars would be staggeringly large. The actual distance to Proxima Centauri is 4.2 light-years, meaning that light, the fastest thing there is, takes 4.2 years to travel from that star to our eyes. We can take quantum leaps upward in universal scale too. The Milky Way galaxy is one of at least 100 billion galaxies in the cosmos. The diameter of the Milky Way's bright disk, which we are in, is at least 100,000 light-years. For comparison, we are a little more than 26,000 light-years out from the galaxy's center. The most distant photons from our own galaxy have been traveling to us for 1/3 of the length of human history. And a little like nesting dolls, we can follow cosmic structures out to larger and larger scales. Our local group of galaxies, as Edwin Hubble termed it back in the 1930s, contains at least 55 galaxies in a sphere spanning about 10 million light-years. Local group members include our nearby friends, the Andromeda Galaxy, and the Triangulum Galaxy. Countless small groups of galaxies are even farther away, and if we travel some 55 million light-years, we get to the center of the largest cluster of galaxies in our cosmic space, the Virgo cluster. This group includes some 300 galaxies of all types, but larger and more massive groups of galaxies lie far more distant from us, nearly countless numbers of them. When we get up to the largest cosmic structures known, we can talk about superclusters and walls of galaxy clusters. Examples include Laniakea, which we belong to, a structure that stretches some 500 million light-years across. And there are dozens of examples of other large structures. So, how big is the universe? According to scientists' estimates, it's around 93 billion light-years. But the 93 billion years is just the observable universe, the universe which we can currently see. The observable universe is likely only one section of the universe, and beyond it there is likely even more space filled with stars and galaxies. The reason why there is an observable universe is because the universe has not existed for an infinite amount of time. Rather, the universe began in the Big Bang some 13.8 billion years ago. A finite age for the universe means that objects beyond a certain point, called the cosmic horizon, are simply too far away for their light to have reached our eyes. Everything we can currently see in the universe is part of our cosmic bubble, called the observable universe. But what about the entire universe? How can we know about parts that are so far away that we have not even seen them yet? That's where things get interesting. By using the Bayesian model averaging, scientists estimated that the universe is at least 250 times larger than the observable universe, or at least 7 trillion light-years in diameter. The bottom line is that the visible universe is incredibly large, and the entire universe is truly enormous. Indeed, the entire universe could be infinitely large. As a result, while we can make estimates as to the size of the universe, scientists can't put a number on it. Scientists then expect we can get closer to the answer with the arrival of James Webb. And more than expected, James Webb, with its remarkable resolution and sensitivity, has allowed astronomers to study the formation of stars and galaxies with unparalleled accuracy. By capturing infrared light, it has unraveled mysteries that were previously inaccessible, shedding light on the early stages of the universe's evolution. However, it took a remarkably long time for the first light emitted by a group of ancient galaxies to reach the James Webb Space Telescope. Astronomers have calculated that the photons were in transit for more than 13 billion years, almost the entire history of the cosmos, before they reached the orbiting observatory. The results are scientifically dramatic and have revealed that the universe was already deep into the process of star formation only a short time after its Big Bang birth. Although the photographs themselves are scarcely stunning in appearance, a handful of smudges, a couple of glowing spheres, and an image that has been described as a glowing dog bone. Nevertheless, the world of astronomy has been dazzled. Among the objects caught in the telescope's giant mirror is one that turns out to be the oldest known galaxy in the universe. The prosaically named JD's GZ14-0 appears as it did a mere 290 million years after the Big Bang, the dawn of the universe. The telescope's previous record holder was a galaxy seen at 325 million years after the Big Bang, which happened nearly 14 billion years ago. The newly observed galaxy is much brighter than expected, suggesting that the first generation of stars were either more luminous or formed much more rapidly than conventional cosmological theories have predicted. As Dr. Francesco D'Eugenio of the University of Cambridge, one of the team behind the discovery, said, "The universe at these early stages was different than it is today. Early galaxies. This is the most distant found, but there are others, seem to be brighter than expected from the models." The unexpected brightness of these early galaxies means that the telescope could make even more distant observations. In the words of Professor Brant Robertson of the University of California, Santa Cruz, we could have detected this galaxy even if it were 10 times fainter, which means that we could see other examples yet earlier in the universe, probably into the first 200 million years. The early universe has so much more to offer. While Webb's breathtaking images of brilliant stars are certainly stunning, one galaxy, an almost indiscernible smudge of light labeled Sears 93316, is causing real excitement among cosmologists and astrophysicists as being reported to be a staggering 35 billion light-years away. At first, it may seem difficult to explain how the distance between our Milky Way and Sears 93316 has grown to 35 billion light-years, given the universe has only been expanding for 13.8 billion years. How can it be that the size of the universe is bigger than its age? Let's delve into. Traditionally, the way you most often think of a distance is by taking 2 points and drawing a line between them. It's something we learn to do as kids and keep with us into adulthood. For most applications, there's no problem in doing this, whether we use a ruler, an odometer, or a light clock. By measuring the amount of time it takes a light signal to take either a one-way or round-trip journey. But this assumption isn't strictly valid when it comes to the universe. Distance isn't necessarily defined by a straight line, nor do those distances remain the same over time. The reason for this is something we don't think about in our day-to-day experience. Space isn't flat, and it's also inextricably linked to time, in the form of space-time. The space isn't flat part is perhaps easier to understand. When you think about the Earth revolving around the Sun, you probably think about it the same way that Newton did, in terms of an invisible, attractive force acting from one object on another. This is the way we thought about gravity for centuries, and it literally took a genius at the level of Einstein to go beyond it. It isn't that mass at a certain distance causes a force, but that mass is a type of energy, and energy causes the fabric of the universe to curve. The fabric of the universe isn't just space, but a quantity known as space-time, where anyone and anything in it experiences space and time together, dependent on how they're moving relative to everything else in the universe. One of the things we learn about a universe governed by Einstein's laws, general relativity, is that it cannot be both static and stable if it has matter in it. A universe that's static, where the overall fabric of space-time doesn't change over time, would be in trouble if you put matter down into it. Over time, that matter would gravitationally attract and would draw itself together towards a point. In a static universe filled with matter, there's only one possible fate: contracting down to a black hole. But don't worry, that's not our fate. Because our universe is doing the one thing it can do to prevent it. It's expanding. The best way to imagine the universe is as a loaf of dough in some zero-gravity oven, where the dough is filled with raisins. Each individual raisin represents a gravitationally bound structure in the universe: a star cluster, a galaxy, a group of galaxies, or something even larger. Each raisin also isn't bound to any other raisin. They are far enough apart that gravity will not bring them together, even given an infinite amount of time. Why? Because the dough is rising, and that dough represents the fabric of space-time. As time goes by, the universe expands, and distant raisins representing galaxies appear to move away from one another. This is the key point that's so hard for most people to understand. The expansion of the universe isn't about a speed. The universe doesn't expand at the speed of light, the speed of sound, or any other speed. If you were to look at a raisin that's close by you, it would appear to move away from you relatively slowly, and a light signal sent from it to you would only take a short amount of time to get there. But if you were to look at a raisin that was much farther away, it would appear to recede much more quickly. A light signal sent from it to you would take a very long time to get there. The reason is because the expansion of the universe depends on how far away an object is from you. It's not a speed, it's a speed per unit distance. This is why, when we talk about the measured expansion rate of the universe, what we sometimes call the Hubble constant, it comes along with such weird foreign values, something like 70 kilometers per second per megaparsec. This tells us that for every megaparsec, or about 3.26 million light-years, a galaxy is distant from any other galaxy. It appears to recede at 70 kilometers per second. So if an object is presently 100 megaparsec away from us, it appears to move away at 7,000 kilometers per second. If an object is 4,300 megaparsec away from us, it appears to move away at around 300,000 kilometers per second, or the speed of light. And if an object is 14,100 megaparsec away from us, it appears to move away at around 987,000 kilometers per second, which is a crazy large number. But there's something you may be glossing over. It appears that these objects move away from us at these speeds. In reality, the objects themselves aren't moving, just like the raisins aren't moving relative to the dough that they're in. Instead, what's happening is that the fabric of space-time itself is expanding, and the light coming from these objects is getting stretched to longer, redder wavelengths as the universe expands. This is why we talk about the redshift of distant objects, because their light gets stretched as the fabric of the universe expands. It's the matter and energy density of the universe that determines how quickly the universe expands, and we have to add up all the different types of energy, including neutrinos, radiation, dark matter, and dark energy, to get the right answer. Today, there's light arriving at our eyes from all sorts of different objects at all sorts of different distances. The objects that are 13.8 billion light years away from us now were much closer in the distant past. When they first emitted the light that's reaching us today, this occurred at a time that was already billions of years ago. That galaxy might be 13.8 billion light years away right now, but the light didn't need to travel for 13.8 billion years to reach us. It traveled a shorter distance and for a shorter amount of time. In fact, we can see objects that are farther away than 13.8 billion light-years today, all because of the fact that the fabric of the universe itself is expanding. So, what do we do if we want to know how big the observable universe is? We just need to ask the following question. Given all we know about the expanding universe and what the different amounts of all the different types of energy that are in it are, how far away would an object be today if its light were only just now arriving after a journey of 13.8 billion years? If you do the math, you get an incredible answer, 46 billion light-years, or 46.1 billion light-years if you want to be even more precise. If our universe had more dark energy and less matter, the answer would be slightly larger. If the universe had more matter and less dark energy, the answer would be slightly smaller. But that's how we get to the edge of the observable universe. This doesn't mean we can reach everything in the part of the universe we can see. The most distant parts of the universe are only visible during the earliest stages. In fact, everything that's more distant than about 4,300 megaparsec or 14 billion light-years today is at the limit of how far we can reach at the speed of light. The object more distant than that can still be seen by us, but only as they were in the past. Similarly, they can only see us as we were in our past. Someone more distant than 14 billion light-years from us, even with an infinitely powerful telescope, could never observe human civilization as it is today on Earth. The fact that we can see the universe we do tells us that it must be expanding. A fantastic match of theory and observation. It also tells us that we can extrapolate back in time to as early a stage as we want, and find all sorts of interesting milestones that happen as far as the size of the universe is concerned compared with its age. When the universe was 1,000,000 years old, its edge was already some 100 million light-years away. When it was just a year old, we could see for nearly 100,000 light-years. When it was just a millisecond old, we could already see for a light-year in all directions. And today, 13.8 billion years after the Big Bang, the farthest thing we could possibly see, corresponding to the light emitted at the first moment of the Big Bang, is 46.1 billion light-years distant. Given the contents of our universe, it couldn't have turned out any other way. Now, let's shift the attention to the recently discovered galaxy, Sears 93316. The light has been traveling from this galaxy for 13.5 billion years. If you could lay down a ruler today, you'd measure its key-moving distance to be around 35 billion light-years. Because the universe was much smaller when the galaxy emitted its light, its angular size distance is 2 billion light-years. Finally, the expansion of the universe decreasing its brightness means its luminosity distance is 615 billion light-years, giving it an incredibly low surface brightness. It should be obvious now why it hadn't been observed until James Webb came along, and its discovery is an impressive tribute to the telescope's light-gathering power. Because of the finite speed of light, we see distant objects as they were when the light was emitted long ago, not as they are now. To many people, this may seem to be a nuisance. Astronomers will never be able to learn what remote galaxies look like right now. However, to cosmologists, it's a wonderful gift of nature. Thanks to the look-back time, they are able to study the early youth of the universe. All you need to do is to look very far away into space, and you're automatically looking far back in time. Thus, the full 13.8 billion year history of the universe becomes accessible to scientific inquiry. Once we hold the whole cosmic history in our minds, we can conjecture different possible fates for the universe, and thus for the end of time. What we do know is that time started with the Big Bang some 13.8 billion years ago. That event marked the beginning of time. We understand time as a measure of change. What changed at the beginning of time is that the universe as we know it came into being in ways we still do not, or maybe cannot understand. However, what changed, scientifically speaking, was that the extremely high density of matter and energy started to be diluted by the expansion of space itself, an expansion that unfolded through time and is still going on. The details of this narrative depend on the kinds of stuff the universe contains. The cosmic recipe determines how the universe changes in time and what kind of future it will have. There are essentially two possibilities. In one, the universe will keep on expanding forever. Because stars have finite lives, at some point, far in the distant future, they will be extinct. Stellar corpses will dot the universe, from slowly smoldering white dwarfs to black holes of different sizes. But drama can be added here, depending on what kinds of matter the universe contains. If the current recipe remains viable, there are three main ingredients: dark matter, dark energy, and the stuff we are made of. The normal matter of protons and electrons. Assuming normal matter and dark matter are stable in the long term, dark energy controls the future of the universe. If dark energy, this ether-like substance of unknown composition, is a constant, that is, if its density does not change and it maintains a fixed volume irrespective of cosmic expansion, then the universe's expansion will keep on accelerating. In extreme scenarios, it may have so much negative pressure that it will rip everything apart, decomposing matter back into its basic ingredients. Instead of from dust to dust, the cosmic epitaph would be from particles to particles. But it is also possible that dark energy is not like that, and that its negative pressure will fade with time, no longer fueling the universe's rapid expansion. Acceleration will lose pace, and the universe will retain the faded stars and their corpses, all resting far from each other, the ultimate cosmic loneliness. The sad part is that in a cosmos without room for entropy to grow, matter cannot reorganize into anything interesting. This is the cold cosmic death scenario. If nothing changes, time itself loses its function and reaches an end. Another possibility is that the expansion will slow down. If there is enough matter out there, it may revert itself and push the universe from expansion into contraction. Eventually, matter that was dispersed for billions of years will compact back into a small volume, heat up, reach crushing densities and, well, it depends. It may go into a big crunch, the inverse of the Big Bang, or it may reach a point of maximum contraction and then bounce outward into a new phase of expansion. This is the bounce universe model, where the universe trades periods of expansion and contraction, never quite reaching the point of infinite density or initial singularity. Time keeps on ticking, although each cycle needs new clocks. Every end of time marks the beginning of a new time, a new cycle of existence. This is a bit more comforting a view than cold death, even if each cycle involves destruction by fire. What we learn from our current cosmological models is how fortunate we are to exist precisely when it is possible to exist. Of course, there is no luck involved here. We exist now because this is when it is possible for matter to agglomerate into thinking blobs like us. In other eras, there would be no stars capable of sustaining life long enough for it to conjecture about its fate. So if time will end, it is because creatures like us will also end. In a universe without sentient beings, aware of time's passage, without the awareness of past and future, the very concept of existence is meaningless. That should give us pause when we consider how small we are in the vastness of space. Small, yes, but as far as we know, we are the ones who hold the whole cosmic history in our minds. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.